We think there's a generational opportunity for AI to transform how advanced industries do the engineering and manufacturing that they do. And I think there's an imperative for that.
Welcome to PhysicsX's London HQ. PhysicsX is revolutionizing engineering and manufacturing through an AI-native simulation platform. In this conversation, CEO and co-founder Jacomo Corbo joins Atomico partner Laura Connell to discuss the story and vision behind PhysicsX.
Giacomo, I'm so excited to be here with you today, and I'd love to kick us off with you telling us a little bit about what PhysicsX does.
Great to be here with you, Lauren. So PhysicsX is a physical AI company setting out to reimagine engineering and manufacturing with AI and physics foundation models. We're building a new engineering software stack, and one that starts from the premise of using AI for physics and chemistry simulation, shifting that simulation from numerical simulation, which is the mainstay of engineering today, to inference.
And, as AI begins to profoundly reshape industrial and physical systems, what makes this inflection point critical, and how does PhysicsX's mission align with that transformation and the timing of that transformation?
Well, across advanced industries, whether you're designing a jet engine or, designing or operating a smelter or a metal castings foundry, engineering or manufacturing has never been more complex. What these enterprises in these different industries are setting out to do is, at a complexity where numerical simulation is just a fundamental bottleneck to operating in these industries. It's why these industries are pretty low productivity. It's why a lot of the engineering manufacturing that they do runs through so many different engineering disciplines that these companies have a great deal of difficulty mobilizing. It's why the capital intensity of, designing things or operating them is so high. So fundamentally, we think that a lot of that has a great deal to do with what engineering looks like today, which is an artifact of what engineering tools look like today. And a lot of that is on a bedrock of numerical simulation. And, insofar as we can relax those constraints and moving things to inference, we think that represents a completely new paradigm for these companies and how they navigate everything that they do, from designing things, designing machines, to manufacturing them, to doing production, to operating assets.
Yeah, amazing. And maybe just to go a little bit deeper on that, you're building large-scale foundation models for physics and geometry. Can you explain maybe what they are and why they're such a big deal for the industry?
Well, fundamentally, numerical simulation hinges on solving equations of physics. These are nonlinear partial differential equations, and solving these by finite differences on some mesh. And, whether we're talking for different classes of physics, for different kinds of chemistry, that's fundamentally what engineering involves. Like, I'm trying to understand some physical phenomenon, I'm trying to predict it, and my ability to predict it runs through solving these complex equations, which takes a whole lot of compute, it takes a whole lot of time, and it's fundamentally a bottleneck to a lot of automation and optimization. What we're setting out to do is to, when we talk about moving into inference, we're trying to get deep learning models to be able to predict it, to sidestep the numerical simulation, the solving of equations of physics. And that allows you to do three things. Like, one, it allows you to be able to much more effectively search really high dimensional spaces. And high dimensional spaces are really a feature of a lot of engineering and manufacturing. And so in the shift to inference, we're talking about accelerating simulation by anywhere between 10,000 to close to 1 million times. What that allows you to do is just bring much more sophistication to how we search these very large spaces. The second thing is it allows us to build models whose fidelity supersedes our first principles understanding of the physical phenomenon. And so, as much as we're training on numerical simulation as most of our training corpus, as most of our training data, we can also condition these models on real world experimental data. So we can do better from a fidelity perspective, from a high, from an accuracy perspective than we could do if we only had the numerical simulation alone. So it's not just about a question of acceleration, it's also a question of fidelity. And maybe the last element, we can take higher fidelity simulation to places where numerical simulation can't go. So think of applications that are compute constrained at the edge. Think of applications that have very strong or short latency requirements. So a lot of manufacturing, a lot of process control. We can bring higher fidelity simulation to the whole engineering lifecycle. And that's one of the things that we're very excited about.
Yeah, I mean, this is fundamentally such a step change in terms of the tooling available historically. Could we maybe just draw out a little bit about how much of a step change this is in terms of what you can do using the platform?
Well, we're starting to see evidence of scaling laws in this domain, which is, a lot what has gotten people excited about in a lot of other domains as well, right? Including with large language models. And if scaling laws continue to hold here, like in the worlds of, physics and chemistry and engineering, fundamentally, what does that tell you? Like in the limit, numerical simulation is going to be used for testing and validation, certainly, but it's also going to be used to train these models, to generate data for them. What we're setting out to do is to have inference be a core part of the workflow in ways that, right now, numerical simulation is in the workflow, is in the engineering and manufacturing workflow, and that's the part that makes it a fundamental bottleneck.
Yeah. One of the things you and I have spoken about before is Europe's opportunity to lead in industrial AI. What gives you conviction in that, and where does PhysicsX really fit into that European picture?
Well, advanced industries, across the board, whether we're talking about semiconductors or automotive materials and energy or, aerospace and defense, it's never been more important to our sovereign interests, to our economic interests, to the sustainability transition. Like across the board, it is so important to industry, to nations, across the West, globally. What we're setting out to do is to enable companies operating in these industries to recover productivity, to do a whole lot more. And I think in that respect, Europe has an incredibly strong advantage, right? Like we have very strong manufacturing companies. We have incredibly strong engineering companies. If you think about what our starting point is, it is companies that are doing this manufacturing, but also that are sophisticated from an engineering standpoint to be able to train these models, to be able to provide the training data, whether it's with respect to geometry and designs or with respect to numerical simulation itself.
Yeah. What's incredible about where you're at already is you're already working in some of the most complex and high stakes industries in the world. Can you give us a sense of the kinds of problems your customers are solving with PhysicsX today, which are by nature global, really, in their application and relevance, and what's behind that early traction?
Well, I would say that high complexity applications, high complexity engineering and manufacturing and production is exactly where numerical simulation represents a bottleneck to optimization, to automation. So as a company, we are specifically selecting into those high complexity applications. They're critical applications, they're very high value engineering. They tally with our thesis that we're trying to change how engineering is done in places where incumbent tools today and where numerical simulation represents a hurdle to jump or a wall to break through. Right now, our whole focus is on very large cap engineering and manufacturing companies. So across these different industries, we started in really discrete manufacturing context. So think more aerospace and defense and automotive. And from there, we've been looking to, think also energy production. So, the likes of turbines, but we've been moving also into process manufacturing industries. Like we think there's a very horizontal opportunity. So, whether we're talking about semiconductors, whether we're talking about aluminum or, metals production, scandium alloy production, processing of different minerals and commodities, the commonalities across these different industries or across applications is that there's complex physics and chemistry simulation in the loop. And so as a company, in the very early rounds, we were building the company on the back of certain technical milestones, working out how to accommodate different physics and chemistry, how to shift those things from numerical simulation to inference, how to build models that would be very good about, to predict those things. As we've done that, it's allowed us to move into different industries, but also to move into, very different kinds of applications as well. And all the tier ones that we work with across these different sectors, these are global companies with very global footprints.
Yeah.
And so, as much as our focus, we've started here in the UK, started, very focused on Europe on the whole, very quickly we got into a place where a lot of that was pulling us into North America and into the US. Today we operate across APAC as well, and it's just a feature of the global organizations that we're working with.
And I think that's one of the most remarkable things about PhysicsX and what you've accomplished already are these proof points around, as you've said, kind of leveraging analogs between verticals. I think a lot of people who focus on simulation have ended up getting stuck in one vertical, and you can build a great business doing that, of course. But already you can see the breadth of verticals that you're able to serve with the PhysicsX platform really does underscore this point you're making around commonality that you find in the underlying physics and your ability to leverage that experience across use cases already today.
Well, if you look at engineering tools today, whether we're talking about CAD or we're talking about shaping geometries, right? Where we're talking about CAE, so computer-aided engineering. So today's tools that help us simulate the physics or chemistry in play, or we're talking about, PLM. Engineering tools writ large are by and large the same across these different sectors. So, they corroborate this view that whatever we are building for one vertical, a lot of that outside of the application layer from a platform perspective, that there's a horizontal opportunity.
Yes.
A lot of what we're doing right now is not being done. This represents a pretty big opportunity for companies across these different sectors. And we are finding a pretty greenfield opportunity. We're finding customers that are meeting real bottlenecks, severe productivity or product performance challenges. Our technology is a pretty good fit for that. We're also a strategic complement to a lot of the investments that they've made into their engineering tools, right? So highly interoperable with a lot of the other CAE tools that they operate, CAD tools and PLM systems,
Yeah.
which motivates this platform play. But we're also setting out to do this across a number of different industrial verticals, precisely because that opportunity exists right now. So we're trying to go after it, and we're trying to, as a company, scale sufficiently quickly to be able to be, effective partners to our very large customers.
Yeah. One of the things I'd like to come back to, and one of the things that is always so integral to how we underwrite investments, certainly, is your journey's pretty unconventional. And from academia to F1 to founding Quantum Black and now PhysicsX, what's the thread that connects all of that, if there is one? And was it a natural path from research and scientific research to becoming a founder?
I mean, if there's a common thread, it's maybe a curiosity, right? And sort of an appetite to learn. And my PhD was in computer science, but it was a little bit more on the theoretical side of things. The things that pulled me into the world of empirics and data science, as it were, was being in Formula One, seeing some of the things that I was doing, just being amenable to solving problems and a pretty broad range of problems in engineering, in a lot of the things that Formula One teams do. A lot of that was the premise for starting Quantum Black, just recognizing that, Formula One teams are, full of incredible engineering talent, whether that's people who know materials and composites and aerodynamics, control systems, vehicle dynamics. A lot of the modeling that they were doing either fell into one of two camps. It was either small scale statistics and, really inappropriate uses of the t-test, for example.
Right. Yeah.
And on the other hand, a lot of structural equations, physics modeling. And, at that point in time, there wasn't all that much data science, all that much, reliance on larger scale statistics and computer science methods. And so having a little bit more of a machine learning background allowed me to go into that world. One of the very nicest things about working with Formula One teams is the technical partnerships that they have with much larger engineering companies. And so, started working with a few very large aerospace companies, including Boeing, in the early days of Quantum Black. And, I spent most of my career in advanced industries, learning a lot about, the amazing R&D and manufacturing that these companies do, but, still approaching it from a pretty horizontal angle, like, trying to find different ways in which evolving methods on the data science side and machine learning side could help solve, some of these problems and challenges and the amazing engineering that these companies do.
Yeah, amazing. And, you built such a rare team at the intersection of AI, engineering and enterprise grade delivery, which is no mean feat. What kind of talent does it take to really deliver on this kind of work, to drive the kind of adoption within the size of the organizations you're working with that come with their own complexity? And who thrives? What kind of a character thrives at PhysicsX?
That's a great question. So I think fundamentally we're not out to replace the engineers that our customers do. They are the ones that understand, best the domains and the hard things associated with doing engineering and manufacturing or running complex machines, doing production in their context. What we found is incredibly helpful is for us to work incredibly closely with them, for us to be able to take requirements for them. Like one of the things that is pretty fundamental to our model is delivery, right? Delivery where we partner really closely with our customers. We really understand what are the requirements and ultimately what are the prospects, like what is the opportunity to go after with a technology that we can deploy. We think the opportunity is fundamentally about refactoring workflows, engineering and manufacturing workflows. It is not about just enabling individual engineers and leaving some legacy process untouched. And so we have a muscle within PhysicsX of engineers who can partner closely with our customers' engineers or manufacturing operators or process engineers, different categories of engineers and different processes, but we'll work closely with them in order to be able to understand, how our technology can have the most impact. And I think from our perspective, for the people here, they get to be exposed to a whole lot of different domains. We're also putting together very cross-functional teams. And so simulation engineers who can understand as much as necessary of the engineering and manufacturing that our customers are doing, but also, machine learning engineers and data scientists who are ultimately implementing the solutions on top of our own software stack and deploying it to production. And from a culture perspective, I think it takes people who have sort of an ingrained curiosity on the one hand and an appetite to learn, also who bring that ethic of continuous improvement. In some sense, we are there to help customers break through walls, right? We're also there to bring conviction that might be possible, right? To these organizations, that are incredibly sophisticated, but that haven't found, a better way. And prima facie, like when we start engaging with our customers, we're doing it on the basis that it might be possible. It's an experiment. There could be a good fit for the kinds of things that we were doing. And if there's one thing that engineers are very good at, is thinking about continuous improvement and continuous learning. Like things that were not possible 30 years ago are possible now. It's why we have reusable rockets, right? And we're trying to bring that innovation, that spirit of innovation to our customers. And I think I think we need almost a brazenness, right?
And an optimism.
And an optimism, exactly, that it might be possible.
Yeah. It's been extraordinary to see the shift in the industry in the last 30 years. So what do you think we have in store in the next 5, 10, 30 years going forward?
Well, we think there's a generational opportunity to transform how advanced industries do the engineering and manufacturing that they do. In the same way that high performance computing changed the complexion of engineering and even the complexity of applications that are possible, we think there's a like opportunity for AI to do the same, and in fact to do it on timescales that are much faster than the way that HPC, high performance computing is, and modern numerical simulation has been adopted on timescales of about 30 years. We think a lot of that will play out in the next 5 years or so, and certainly for large cap engineering companies. And I don't think that's something that will necessarily happen one sector at a time. We're trying to make this possible across a number of different industries incredibly quickly. And I think there's an imperative for that. There's an imperative for that just because, it costs between $8 and $10 billion to design and build a new smelter. It costs $4 billion to design a new jet engine. And it takes between 7 and 10 years to develop, the largest jet engines today. It's between 12 and 15 years to build a hypersonic aircraft. Those are timescales that the world just can't wait for. And so we're trying to accelerate a lot of the development and manufacturing to drive down its capital intensity. And I think it's an imperative for these industries, but I think also there's an opportunity to be able to do that with the technology that's being developed right now.
Yeah. PhysicsX has such an exciting role to play in this. Looking ahead post Series B, what's your outlook for the next phase of growth and perhaps some of the milestones that you're most focused on for the company?
Well, I think, you know, in the first place, we're setting out to, to scale and to grow, right? We want to be good partners to the very, very large enterprises that we serve and work closely with. So certainly we need to get bigger, right? So we can be an effective force multiplier to them and all the engineering and manufacturing that they do across the global footprint that they have. We're also building larger and more capable physics foundation models. So certainly continuing to do that, continuing to make those models more effective and so that they meet the complexity of the engineering that our customers do. That's, an incredibly important part of it. And maybe the last element is for us to be able to have the footprint that we want to have across the critical sectors. We're going after aerospace. We're going after semiconductors. We're going after automotive. And we're going after minerals and materials and energy.
And we feel incredibly privileged to be part of that journey going forward. Jacomo, thank you so much for taking the time to walk us through things today. It's been a real pleasure as ever.
It's a real pleasure to work together.